Hi everyone, this is Mrs. G, and today we're going to learn how to graph and solve absolute value functions. So before we get started, please pause the video and give this warm-up a try. Sorry, the formatting got a little messed up. Here's a part C function down here. All right, let's go ahead and check our answers here. So remember, the way we check for even, odd, or neither is you substitute negative x into your function. If you look at part A, if you substitute negative x and simplify, and what you get is the same as your original function, so f of negative x equals f of x, the graph is even. Let's skip to part C for a second. If you substitute negative x and you simplify, and the result is the exact opposite of the function you started with, meaning every term has an opposite sign, so notice positive x cubed turned to negative x cubed, positive 4x turned to negative 4x, we can say that f of negative x equals negative f of x. So the opposite x value gives you the exact opposite y value. We would call this type of function odd. And if you substitute it and neither of those cases work, we would say that's neither. So if you look at this case, compare it to the original function. X squared is the same, but the negative 3x became opposite. So half of it is opposite, half of it is the same, so this is neither. All right, so now we're going to start talking about absolute value functions. So to start, let's do a quick sketch of what the parent function would look like. So absolute value of x. So let's do a quick t-chart. So we can do maybe -2, -1, 0, 1, 2. So when you substitute in, remember absolute value means the distance from that x value to 0. And distance is always positive. So essentially turns negative values positive and positive values stay positive. So the absolute value of -2 is +2, so on and so forth. So these would be our coordinates. So we have -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, and it continues on like this. So this is what our absolute value graph looks like. So if we're thinking about it in terms of transformations, this would be the general form. So f of x equals a times the absolute value of x minus h plus k. Some key features, it is always going to be a V-shaped graph, and it's going to have a vertex at hk. So notice in this form, it says x minus h, and the vertex is at positive h, so these are always going to be opposites. These will be the same. And this goes along with transformations, right? If we translate left or right, up or down, it's going to move where our vertex is. Another key feature is that absolute value graphs are really a combination of two linear functions, one on either side of your vertex. So you can see this is its own linear function going to the right, and this would be a different linear function happening on the left. The slope to the right of the vertex is always going to be that coefficient here. So when it's just a 1, you can see the slope going to the right is +1, up 1 over 1. And the slope going to the left is going to be the opposite of whatever this coefficient is. So you can see to the left of my vertex, the slope of this line is -1. So an interesting case when we're working with absolute values, let's consider these two scenarios. So if we were looking at this in terms of transformations, we would call that 2 a horizontal shrink by a factor of 1/2. So again, here's some points from my parent function. It looks like this. This is our parent function. So imagine we're graphing this using transformations. Since it's a horizontal shrink by a factor of 1/2, all of our x values would get multiplied by 1/2. So let's see what that would look like. So again, all of my x values have been multiplied by 1/2. There you go. So you see that you get a narrower graph. Now let's look at this function, f of x equals 2 times the absolute value of x. So for this one, we would call it a vertical stretch by a factor of 2. So again, here's my parent function. So let's imagine we take all of our y values this time and multiply them by 2 because it's a vertical stretch. So this point goes to here. 2 goes to 4. And then it's already off our graph, so it does look something like this. So again, all of our y values were doubled because it's a vertical stretch by a factor of 2. Now look at these two graphs. You actually have the same exact graph for two seemingly different transformations. So in the case of an absolute value function, sometimes a horizontal shrink might give you the same result as a vertical stretch, or vice versa. So my recommendation to you is anytime you have a absolute value function with a horizontal stretch or shrink, we can actually simplify this. We know that the absolute value of 2 is just 2, so we can actually rewrite this function or this equation to look like this. So again, anytime we are working with a horizontal stretch or shrink, let's simplify to graph because it makes it a little bit easier to work with a vertical stretch or shrink. Okay, so let's try graphing the following absolute value functions. We can graph this using transformations, but I do have maybe a little trick for you guys to make it quicker. So whenever we're graphing an absolute value function, the first thing we can look for is the vertex. So remember that vertex is always going to be at hk. If you remember that general form we talked about on the previous slide, it looks like this. A times the absolute value of x minus h plus k. So you can look here and here for your h and k values. So this is plus 2, so that means that your h value is negative 2. Remember, it's opposite. And since I don't see anything here where k would be, that means my k value is actually 0. So this graph has a vertex at negative 2, 0. And then you look at this number out front, it's positive 2/3. So that's going to be the slope going to the right. So from my vertex, I just go up 2 over 3. And then we make the opposite, the slope going to the left. So on the left, our slope is going to be negative 2 over 3. So we can kind of work our way backwards, and we get a graph that looks like this. So this graph has a slope of negative 2 over 3. And there you go. So we don't have to make a t-chart. We don't even have to use transformations. We can just find the vertex and then follow this slope going to the right and follow the opposite of that going to the left. Let's look at this one together. So let's start with our vertex. So remember, it's at hk. So it's going to be positive 1, positive 4. So we can start there. This negative 3 is going to be our slope going to the right. So this one's actually going to be an upside down V. So again, start at your vertex and go down 3 over 1. This is always your slope moving towards the right. So it will look like this. And then we do the opposite of this slope going to the left. So on the left, our line will have a slope of positive 3. So we can work our way backwards like this. So you can see this portion of our graph has a positive slope. Let's try another two together. So here we have a horizontal stretch or shrink with a shift. So there's a few extra steps we need to do before we graph. So first, we need to always factor out any horizontal stretch or shrink from this binomial. So we're going to rewrite this as the absolute value of 4 times x minus 3, then the minus 5 is unaffected. And then this we can actually simplify. We know the absolute value of 4 is just positive 4, so we can actually move that to the front of our absolute value sign. And this graph is exactly the same as this graph, but this is just a little easier to work with. So this graph has a vertex at 3, negative 5, so we can start there. And then we follow a slope of positive 4 going to the right. So we go up 4, right 1. And then we have a slope of negative 4 going to the left, like this. All right, let's look at part B. So same thing, we need to first factor out that negative 2. So when I factor out negative 2, this actually becomes x minus 1. Be careful for that change in sign. And then here we can simplify this. The absolute value of negative 2 is actually positive 2. So positive 2 times the absolute value of x minus 1. So if you're worried about the fact that we once had a reflection and then all of a sudden we don't, consider what type of reflection this is. This would be a horizontal reflection over the y-axis. Absolute value functions are already symmetrical about the y-axis, so a horizontal reflection actually doesn't do anything to our graph. So that's why it can disappear and our graph is essentially unchanged. So here we have a vertex of positive 1, 0. We follow a slope of positive 2 to the right, and then a slope of negative 2 to the left. All right, go ahead and pause the video and give this one a try. Sorry about the formatting. This is the function for part B. Okay, go ahead and check here. So for part A, the vertex should be at 3, 2, and it has a slope of negative 3/2 to the right, and then a slope of positive 3/2, everything to the left of the vertex. And for part B, remember here, we're always going to simplify this. So first factor out the negative 5, and then we can simplify this because the absolute value of negative 5 is positive 5. So our vertex is at negative 2, negative 3, and a slope of 5 to the right, a slope of negative 5 to the left. Okay, so now we're going to look at pictures of graphs and see if we can describe what we think the function should be. So for this first one, we can always start at where that vertex is. So we see that our vertex is at 1, negative 3, so that's going to be our h and k value. And then we can just look at the slope going to the right. So we can see the slope going to the right is positive 1/2, is rise over run. So that's going to be that a value up front. So we could say f of x equals 1/2 times the absolute value of x minus 1 minus 3. Okay, let's try part B together. So our vertex is here at 0, 4. So that's again going to be our h and k values. And then let's look at our slope going to the right. So we can say from here to here, we can see that our slope is negative 3. So that's going to be that a value out front. So we could say f of x equals negative 3 times the absolute value of x. H is 0, so we don't need to add or subtract anything. And then plus 4. Okay, so I want to talk about kind of a new concept that ties in to absolute value functions, and this is the concept of what's called a piecewise function. So a piecewise function is a function that consists of different pieces of individual functions over different intervals of x. So a piecewise function could look something like this, where you can see, okay, I have one function in this region, and then I have a different function in this region. They don't have to only be linear functions. They could be quadratic or any type of function over any interval. And then this is how we write a piecewise function. So we say f of x equals, then we do our nice, like a big, tall, fancy bracket. And then we're going to describe the equation of each part of our function over the interval. So you can see that in this graph, we have a positive linear function, everything greater than 0. So we could say the equation of this portion is x plus 3. And then here you can see we have a negative linear function, so that's the negative x, and that's for everything when x is less than or equal to 0. So again, it's just describing a bigger function in terms of smaller pieces that exist over different intervals. So this is a function. It's just simply not a continuous function because it has that jump, but it is a function, and we can describe it as a piecewise function. So the reason why we are talking about piecewise functions is because you can actually think of any absolute value function as a piecewise function. So one function to the right of your vertex, one function to the left. Let's add little arrows on this. So we're going to practice actually writing this as a piecewise function. So here we're just given the graph. So we can say, okay, we're going to describe everything to the right of our vertex and everything to the left of our vertex. So let's set up our piecewise function. So f of x equals, and we'll do nice big brackets. So let's start with everything to the left of our vertex. So we're going to do everything up until this point at x equals 2. So this linear function has a slope of -1 and a y-intercept of 3, 0, 3. So we can describe this as negative x plus 3. Again, that describes this line. And this is for the interval of everything less than 2. So we'll say for x is less than 2. Now we could include the vertex as part of this function, or we could include it as part of this function. We just can't include it in both. So I'll say let's include it for the other part. If you would like to include it for this part instead, that's fine. So now let's create the line of, or the equation for this function. So this part of our function has a slope of +1. If you continued that on, it would have a y-intercept at 0, -1. So we could say it's x minus 1 for everything when x is greater than or equal to 2. So again, I included 2 for this bottom part of our function. If you would like to include it for this part of our function instead, that is completely fine. Okay, let's see if we can do the same for part B. So for part B, we're just given the equation of the function. So for this, it might actually be helpful to sketch a little graph so we can visualize what's going on. So this has a vertex at -1, 0. So let's say somewhere right around here. Just a rough sketch will help us. And then it has a slope of -1/2 going to the right and +1/2 going to the left. So we go down 1/2, down 1/2, and then going to the left, again, it has a slope of +1/2. Okay, so now let's describe the two linear equations we see here. Let's start with the part on the left. So here we know what the slope of our line is, but let's say, we don't see what the y-intercept is, and maybe we're not sure just by continuing on. So let's actually see if we can make this equation in a different way. So hopefully we remember that point slope formula. It looks like this: y minus y1 equals m times x minus x1. We can use this point slope to make our equation because we have more than one point and we know that the slope is 1/2. Okay, so let's make that equation. So we know again that the slope is 1/2, and we can use either of these points. Let's use the point -1, 0. So let's plug this into our function. So y minus y1 equals m times x minus x1. So we get y equals 1/2 x plus 1/2. Again, we could have seen that by carrying on our slope. We would know that it crosses at 1/2. But this is another way we can make any linear equation as long as we know, again, the slope and any point on the graph. So we have f of x equals, set up our piecewise function. This is the function for everything when x is less than or equal to -1. This time I'm going to include the vertex in this portion. Again, we can include it in either half, just not both. So pick one or the other. Okay, now let's make the equation for the part going to the right. So we can use the point slope again, or we should just be able to see, okay, my y-intercept is at 0, -1/2. So we have a slope of -1/2, so -1/2 x minus 1/2, and that's for the interval x is greater than -1. Again, if you would like to include -1 in the second interval, you can. You just cannot include it in both. So there we have it. We have our piecewise function written for both of these absolute value functions. All right, so at this point, I'm going to ask you to pause the video and see if you can give these two a try. And then when you're ready to check, just hit play. All right, go ahead and check here. So for our first one, everything to the left of 0, this line has a slope of 2 and a y-intercept at 0, 4, and everything to the right or including 0, this has a slope of -2 and also y-intercept at 4. And for the second function, if you do a quick sketch, you can see it looks something like this. So everything to the left of our vertex, which is at x equals -5, this graph has a slope of -3/5, and if you continued on that slope, you'd see we have a y-intercept at 0, -6. And to the right, we have a slope of +3/5, and it actually goes through the origin. That's our y-intercept. All right, so now that we know how to graph absolute value functions, now we're going to talk about how to solve absolute value equations. So we can do this both graphically and algebraically. So for graphically, we actually graph each side of our equation as 2 individual graphs on the same xy axis, and then we look for the points of intersection. So our answer is just going to be the x values of the points of intersection if they exist. If we're solving algebraically, we're going to first isolate the absolute value term. So we're going to remove anything that's not within the absolute value term. And then once we've done that, we can actually create 2 separate equations, one for the positive case and one for the negative case, which would eliminate our absolute value signs. And then we just finish solving. One important thing to note, an absolute value expression cannot equal a negative number. So if you ever have a scenario where you've isolated the absolute value term and it equals a negative, that will be a case where we actually have no solution. So it's very possible with these types of equations to get 2 answers, but it's also possible to get 1 answer, 1 solution, or no solution. All right, let's try one together. We're going to solve this equation both graphically and algebraically. So let's start with graphically. So we're going to actually graph this absolute value equation that's just on the left side. So we're going to graph 1/2 absolute value of x minus 3 plus 4. And then we're going to graph the equation on the right, which is a constant function, and then we're going to see where they intersect. And for this, let's change the scale. I'm going to change the scale on my x and y axis to count by 2's. Okay, so let's start by plotting our vertex. Our vertex should be at 3, 4. So our vertex will be right here. And then the slope going to the right should be 1/2. So up 1 over 2, up 1 over 2, up 1 over 2, like this. And the slope going to the left should be -1/2. Like this. So in blue, that's just this portion of the equation. And now in red, I'll graph this portion of our equation, which again is just a constant function. So it's just y equals 6, which makes a horizontal line at 6. So it looks like this. And then we just look to see where they intersect. So you can see that we intersect here and here. So we're going to take the x values of those coordinates. So we would get x equals -1 and x equals 7. So 2, 4, 6, 7. Again, we just take the x values of where our functions intersect. So now let's solve this algebraically, and let's see if we get the same solution. So first, our goal is to isolate this absolute value. So we can start by subtracting 4 from each side, and then multiplying each side by 2. Okay, and now at this point we can create our 2 separate equations. So one for the scenario where the absolute value of x minus 3 is positive. So we would just say x minus 3 equals 4. And then one for the scenario that whatever's inside our absolute value is negative. And so then we can put that negative on the other side. So we get x minus 3 equals -4. So we no longer need our absolute value signs. So we finish solving and we get x equals 7 and x equals -1. So we get the same 2 solutions whether we solve it graphically or algebraically. All right, go ahead and pause the video and give this one a try. Again, please solve it both graphically and algebraically. All right, go ahead and check your solutions here. Whether you solved it graphically or algebraically, you should get two solutions, 0 and -2. Okay, let's try another one together here. So let's start by solving this graphically. So let's graph the left side of our equation. This has a vertex at 4, 1. And it has a slope of 5 going to the right. Goes a little off our graph, but that's okay. And -5 going to the left. So it looks something like this. So it's the right side of the equation, and the left side of the equation is the constant function y equals 1. So it looks like this. So you can see here we have a case where we have just one solution, which happens sometimes with these types of equations, and that singular solution is x equals 4. So that's what it looks like graphically if the constant function happens to intersect at the vertex. Now let's solve it algebraically so you can see what that looks like. So again, let's isolate our absolute value expression. So absolute value of x minus 4 equals 0 when we isolate. So here we can set up two equations, one for the positive, one for the negative, but 0 is neither positive nor negative, so really it just becomes one equation, x minus 4 equals 0, so x equals 4, because again, the positive version of 0 is the same as the negative version of 0, it just stays 0. So that's what it looks like algebraically when you only have one solution. All right, we're going to do one more example together. So let's start by looking at this graphically. So the left side of our equation, this has a vertex of -3, 4. And then it has a slope of 2 going to the right. Again, it goes a little off our graph, but that's okay. And a slope of -2 going to the left. And then on the left side of our equation, or sorry, the right side of our equation, we have the constant function y equals -2, which is way down here. So you can see here, the left side and the right side of our equation do not intersect at all when we graph them. So this is a case where we have no solution. Let's see what that looks like algebraically. So again, let's isolate our absolute valued term. Absolute value of x plus 3 equals -3. So remember I told you an absolute value expression can never equal a negative because that's the purpose of the absolute value. It would actually turn anything that is negative into positive. So again, it's impossible for any absolute value term to equal a negative number. So when you see something like this, you say, okay, that's not possible, and we would say this is no solution. So now you know what to expect, both graphically and algebraically, when you have this scenario. Okay, that is all for today's lesson. Thank you so much for watching.